Welcome to this technical summary on high accurate and efficient numerical algorithms for the self-consistent field theory. In this presentation, we explore state-of-the-art computational methods devised to solve the self-consistent field theory problems with improved accuracy and efficiency, which are crucial for simulating molecular assemblies in polymer science and other fields. This work addresses the challenge of efficiently and accurately solving the self-consistent field theory, or SCFT, equations that describe the behavior of polymeric systems and other complex molecular assemblies. SCFT is a powerful theoretical framework widely used in soft matter physics and materials science to predict phase behavior and structure formation. However, it demands solving nonlinear equations that can be computationally intensive, especially for high-dimensional systems. This paper focuses on improving iterative numerical algorithms for SCFT. Their goal is to design methods that accelerate convergence to saddle points in the SCFT iteration while maintaining high accuracy. They also consider a technique known as optimal computational domain, which automatically adjusts the simulation box's size and shape for better efficiency. The approach includes comparing different nonlinear iteration schemes, such as the alternating direction implicit ADI method, Anderson mixing AM, and an adaptive Anderson mixing AAM method. Further, the paper tests the incorporation of a coarse mesh nested iteration, or CML technique, to speed up convergence. Finally, the authors examine the self-assembly of polymer phases in higher dimensions, using these advanced numerical tools to reveal accurate morphologies and phase transitions. This summary will guide you through the core figures, highlighting the iterative procedure, efficiency comparisons, and self-assembled phase structures predicted by these computational advances. Figure 2 presents the flowchart of the self-consistent field theory iteration process employed in this study. The complete SCFT iteration consists of multiple components, including the saddle point iteration, the coarse mesh nested iteration, or CML method, and the approach to optimize the computational domain automatically. This flowchart outlines how these steps interplay to solve the nonlinear self-consistent equations efficiently. The iteration involves initial guesses, updates to field variables, and convergence checks to progress towards the saddle points. The integration of the CML technique allows the method to start computations on coarser grids before refining successively to finer grids, improving computational efficiency. Additionally, the scheme includes optimal computational domain adjustments to adapt the simulation box size and shape dynamically, which improves accuracy and computational cost balance. The authors interpret this flowchart as a comprehensive framework that seamlessly combines these components to yield high-accuracy CFT results within reduced computational effort. In Figure 5, the authors compare the performance of 3 iterative methods applied to accelerate SCFT convergence: the alternating direction implicit, or ADI scheme, the Anderson mixing, or AM method, and the adaptive Anderson mixing, or AAM method. The parameters used in this comparison include chi-n equal to 16, eta n 8, volume fraction 0.6, lambda 100, beta 2, and discretization nodes nr 32 and theta 8 and n phi 17, with the contour discretization ns set to 200. The numerical tests are based on a 4-dimensional case, incorporating 1 spatial dimension, 2 orientational dimensions, and 1 contour dimension. The figure shows the convergence behavior for each method in reaching the saddle points of the SCFT iterative process. All 3 methods are able to converge, but their rates differ appreciably. The ADI method shows the slowest convergence among the 3, requiring more iteration steps to meet the target accuracy. The Anderson mixing method improves on this, showing a faster rate. The adaptive Anderson mixing method converges the fastest and requires fewer steps than standard Anderson mixing, thus representing the most efficient technique among those tested. The authors interpret these results as demonstrative of the effectiveness of the adaptive scheme in accelerating nonlinear SCFT iterations with robust convergence. Figure 6 compares the adaptive Anderson mixing method, or AAM, with its accelerated version that incorporates the coarse mesh nested iteration, called AAM-CML. Using the same base parameters as before, the authors choose a coarsest grid with dimensions 16, 9, 450 for NR, N-chi, N-theta, and NS respectively, with 3 levels of grid refinement. Each grid level achieves progressively tighter error tolerances set as 10 to the -4, -6, and -7. The figure displays the SCFT iteration error for both the standard AAM method and the AAM-CML method across iterations. At each transition to a finer grid, the iteration error jumps noticeably but decreases quickly to the required accuracy tolerance, showing effective convergence. Importantly, although the AAM-CML method may take more total iteration steps to achieve convergence, it drastically reduces the actual CPU time required. The authors cite a 63.88% reduction in CPU time compared to the original AAM method, as summarized in their Table 6. This demonstrates that the coarse mesh nested iteration technique substantially accelerates SCFT computations by initially performing calculations on coarser grids before refining. The authors interpret this as a significant improvement in computational efficiency without sacrificing accuracy. Figure 7 illustrates 2 ordered phases obtained from the SCFT calculations, the pneumatic phase and the smectic C phase. The figure consists of 3 columns for each phase representing the density distributions, orientation distributions, and schematic molecular arrangement diagrams. For the pneumatic phase, seen in panels 1A, B, and C, the density distributions phi A and B show expected compositional profiles, with phi A equal to the volume fraction F and phi B as its complement. The orientation distribution of semiflexible blocks at position Z equals 0 displays parallel alignment, characteristic of the pneumatic phase where molecules tend to orient in the same general direction without positional order. This is visualized in panel 1C with a molecular schematic. In contrast, the smectic C phase results, shown in the second row of the figure, feature density and orientation distributions that peak at angles theta within the interval between 0 and pi2. This confirms a tilted molecular ordering typical of smectic C, where layered structures with molecular tilt are present. Panel 2C shows the corresponding molecular schematic arrangement. The authors interpret these visualizations as successful reproduction of these distinct phases by their numerical model, demonstrating the capability of the algorithm to capture complex orientational and positional ordering phenomena in polymer systems. Figure 8 explores columnar morphologies formed by flexible semi-flexible diblock copolymers in 5-dimensional SCFT calculations. The figure displays from top to bottom the density distributions of monomer type B, fast Fourier transform or FFT patterns, and orientation distributions of semi-flexible chains for 3 distinct tiling patterns labeled as 4436 and 34.438. These naming conventions follow Archimedean tiling rules, describing geometric arrangements of polygons composing the structure. For example, 44. Tiling is interpreted as repeating square polygons cyclically touch at vertices, marked by monomer B at higher concentrations, forming these vertices. The authors reproduced the previously reported 44 and 36 patterns, while also discovering a more complex new morphology, denoted as 34-438. Detailed model parameters for these calculations are given in Table 8. The FFT patterns reveal the underlying symmetry of each morphology in reciprocal space, confirming the ordered structure. The orientation distributions demonstrate the semi-flexible block alignment within these patterns. Together, the results indicate the numerical algorithm's ability to capture intricate, higher-dimensional self-assembled morphologies with molecular orientation information, which is crucial for understanding material properties. Figure 9 extends the SCFT computations to 6 dimensions, enabling the study of 3-dimensional cubic structures composed of rigid polymers. The figure presents 4 distinct morphologies: body-centered cubic or BCC, face-centered cubic or FCC, double gyroid or DG, and single gyroid or SG phases. Each phase is illustrated with 3 rows. The first shows the 3D spatial morphology, the second gives a top-view projection of the density distribution, and the third displays the corresponding orientation distributions of the polymer chains. The careful selection of parameters listed in Table 9 allows the numerical method to successfully simulate these complex phases. The BCC and FCC phases exhibit characteristic cubic symmetry with distinct packing of polymer domains. The gyroid phases display bicontinuous network structures with unique topology and chirality, distinguishable by their orientation patterns. These results showcase the algorithm's capability for predicting sophisticated microstructures in three spatial dimensions while incorporating molecular orientation effects. The authors interpret these findings as a validation of their numerical approach for handling high dimensionality and complex ordered phases. Figure 10 demonstrates the process of SCFT iteration combined with optimization of the computational domain, starting from lamellar phase initial values. The domain optimization dynamically adjusts the simulation box's size and shape, with error tolerance set at 10 to the minus 4. Using fixed parameters such as key n equal to 18, f.75, IN9, Lela 300, beta 2, and discretization nodes NR20, N theta 8, N0, Ns 100, the lamellar phase structure evolves through the iteration process. The figure shows how the system transitions gradually to a more complex 6-phase as the computation proceeds. This transition is captured on the left-to-right sequence of visualizations in the figure. The authors track metrics, such as the angle between domain edges and lengths of domain sides, to illustrate that the optimized computational domain changes shape from square to rectangular, accommodating the new phase. This adaptive domain approach helps to minimize free energy H during the process, which converges as iteration proceeds. The authors interpret this as effective evidence that their optimization scheme can automatically find the most suitable computational box geometry to capture varying self-assembled structures accurately and efficiently. Figure 12 shows another example of SCFT iteration combined with computational domain optimization, this time starting from the 36-phase initial domain and transitioning to the 44-phase. The domain changes shape from rectangular to parallelogram as the method optimizes domain geometry for the new phase. The model parameters remain consistent with prior examples, including key n at 18, f.75, and other discretization settings as before. The figure visually presents the phase transition process from left to right, capturing how the computational box adapts to support the emerging 44 morphology. This automatic adjustment reduces user intervention and ensures that the domain shape closely fits the periodicity and symmetry of the self-assembled phase. The authors interpret this result as further validation of their approach's capability to find optimal simulation domains consistent with previous findings and demonstrating robustness across different phase transitions. In conclusion, this work presents a comprehensive numerical framework to solve self-consistent field theory problems with enhanced accuracy and computational efficiency. By comparing classical and advanced iterative schemes, the authors demonstrate the superiority of adaptive Anderson mixing for faster convergence. Introducing the coarse mesh nested iteration method further speeds up computations by enabling interpolation from coarser to finer grids without losing accuracy. Another critical advancement is the automatic optimization of the computational domain shape and size, which is essential for accurately capturing complex self-assembled polymer morphologies. The numerical methods successfully reproduce various ordered phases, including nematic, smectic C, columnar Archimedean tilings, and sophisticated 3D structures like gyroids and cubic packings. These capabilities highlight the versatility of the approach for simulating a wide range of molecular self-assembly phenomena, spanning multiple spatial and orientational dimensions. Overall, the integration of these high-accuracy, efficient numerical algorithms offers a powerful tool for exploring polymer physics and materials science. This work sets a foundation for future developments in SCFT computations, enabling better prediction and understanding of soft matter structures with reduced computational cost and improved reliability.